Here's an example in section 4.4. We are going to consider the function f of x equals 2x cubed minus 18x. On what open intervals is the function concave up, and on what open intervals is it concave down? So let's start by taking some derivatives here. Okay, so there's our original function, f of x. You can tell that labeling the function and its derivatives is pretty key on this. We want to keep the function and its derivatives straight. So first derivative, make sure you're very clear with that prime notation. F prime of x is going to be 6x squared minus 18. And then our second derivative, which we know we're going to need because we are looking at concavity here, and concavity relates to the second derivative. So f double prime of x is going to be 12x. Okay. Now, for testing our second derivative, remember that for testing, we want to look at where the second derivative is undefined, and also where the second derivative equals 0, because we could have inflection points there. Now, these are very similar again to critical points, okay? But I'm just going to say that these are potential inflection points, since we're working with the second derivative. For some reason, they don't call these critical points when we're looking at the second derivative. They don't have a very fancy name or anything. So potential inflection points are where f double prime of x equals 0. We can also note that f double prime of x is never undefined here in this case. All right, so we want to see where 12x equals 0, and of course that's going to be at x equals 0. Okay, so for testing of our second derivative, we're going to set ourselves up with a number line, and I'm going to label that number line to show us what is being tested there, f double prime of x, which is 12x. And we're going to put our notable point on here where f double prime of x equals 0. I'll make a little note of that. Okay, so that happens at 0. And then you're going to test values on either side of that. So you're testing in these two different intervals. And remember with this, you can pick a value of x, or you can think about general values, what's going to happen there. You might pick something like -1 over here, any negative number to test this interval, all right? If you plug it in to your second derivative, in this case, we would get -12 if you're testing x equals -1. But the main idea there is that that is a negative number. Okay, so in this whole interval, the second derivative is negative, and negative is going to correspond to being concave down in that interval. Then you move to your other interval, think about some positive value over there, test that in your second derivative. I did x equals 1 just kind of as a nice default there, and we get a positive second derivative. Any value you would have picked over there would have given you a positive second derivative. And positive corresponds to being concave up. So we can label our intervals here. Places where the function is concave up is going to be over here from 0 off to infinity. And notice it does say specifically open intervals, so that means we are not going to include 0, because at 0, the function is not really concave up or concave down particularly. It's like both and neither at the same time. So don't include 0 in that interval. Put a parentheses on it, not a bracket. And then concave down, that will be our other interval over here from -infinity up to 0, like so. And that would answer the question, but we might as well also note here that we do have an inflection point with this function. We have an inflection point at x equals 0, which corresponds to a point value, okay, f of 0. If you plug it back into the original, f of 0 would be 0, okay? So we have a inflection point at the origin, 0, 0. All right, now really quickly, let's look at a graph of this function. So let me grab our function here, math it up. Let's see why it's being wonky there. Fix that little 3 and I think it'll like it better. 2x cubed minus 18x. Okay. No. Does it like it? Yeah, it likes it. Okay, so let's look at our graph. Now, they are giving us, boy, a pretty lousy graph there. Let me see. I might need to graph this on some better graphing utility where I can zoom out and show you the y direction a little easier. But I think we might actually have a graph of this in our previous section. Let's bop back to 4.3 for just a second. Yeah, there it is. Okay, so here was our, oh, we didn't graph this, but we did find where it was increasing and decreasing. So here's an experiment for you as you're watching this video. Graph this function, f of x equals 2x cubed minus 18x, and see that it matches up with our ideas of increasing, decreasing. We found the local maxima and minima, all right? And then also make sure that it does match up with these intervals for the different types of concavity. It should show a concave up shape from 0 to infinity and a concave down shape on the rest of the graph. So that'll be a nice little experiment to look at there. I'll make sure we graph the next one. So stay tuned for the next example video, and we'll actually graph this guy when we've identified all these different things about that function.